the additional thing is that we may have parameters in the constructor in some sense. Okay, this is what we have here. Let me see. Yes, even here. Let's go back here. So, okay, even. You see that even. Okay, it's basically quite similar to a list actually. Okay, you have if you forget about the fact that even as a parameter, just think a little bit about that. Forget about this parameter here. Okay, so you can say that you have even, forget the parameter, and you have a number n, then an even concludes to an even. It is very similar to a list. It is actually a list of numbers. It is a list of numbers which happen to be all even. Okay, actually, it's not any list. It is a list which has a shape 0, 2, 4, 6, something like this. Okay, this kind of list. If you look at again, you look at this tree here. Okay, so you have to see the list in the sorry. Okay, this is at the root. So you have so the list is here. So forget about this one. The list is made of 8, 6, 4, 2, 0. This is the corresponding thing. I will write. Okay. So this is similar to. I will write it with cons. Maybe cons of 8, cons of 6, cons, okay, of 4, cons of 2, and nil. So nil plays the role of E0. Okay. Again, so remember this expression here. And if I type even 10, sorry, here, okay, look at even 8, 2, 6, 2, exactly the same. Okay, just look at something. No, there are nothing implicit. No, okay, so that's exactly the same actually. Yes, what is hidden is the fact that it's like a list, but this list is forced to have arguments. Its elements to be in this kind of order. I cannot say that cons of 5 followed by cons of 7 followed by cons of 10, etc. Something with any number would be a proof of even. But any proof of even is a kind of very special list made of okay, so of natural numbers which have this kind of sequence. Okay. Okay, and once you understand that, the important point is that you can reason about proof trees in the same way as you could reason on lists or on trees, and this is what we will do right now. So consider this other predicate here, which is like okay, similar to I have this time 3 constructors. So okay, I wrote this way because I didn't want to write S of S seven times. You could not see exactly how many S you have. So it is easier to read this way. Okay, but remember that this is really like S of S, etc. Okay, so this one, it is exactly the one we could use for even. So it is like even. Exactly. So if I stop here, it is really like even. Okay. But I add this possibility here, which means that okay, I could either add 2 or add 7. Okay. So for instance, I can prove that 11, okay, is accepted by this predicate. Okay. So so why? Because I can make 11 by taking 2, adding 0, then plus 2 plus 7, or 0 plus 7 plus 2 plus 7. Okay, you know what I mean. I can choose different ways to make the proof. Okay, so let us do that. Method 1. So I could say so apply, for instance, PP2. Okay, then apply PP2 again. Okay, and then if I apply PP2, I am dead. I cannot, but I know I can apply PP7. Okay, and apply PP0. Okay, so, okay, method 1. Okay, another one. Okay, so I will take this one, but I will use a different order. For instance, here I make 7 and 2 here. Okay, so PP2, 9. Here I use PP7, 2, PP2, and 0. Okay, and okay, and so you see the ID. And the last one, I will start with PP7 for the last one. So what you see is that an interesting thing behind that is that usually in math we're only interested in provability. Is it possible to prove some statement? Okay. In constructive mathematics, we can also distinguish between different proofs of the same statement. All these three proofs are different. I cannot claim that this one is, sorry, that this object here is equal to this one and is equal to that. That's wrong. You can just print all of them. So okay, let us see them one by one. You will see very clearly on the output. So the first one, okay, maybe it's a little bit too large. Okay, like this. So this is this list. Okay, a list made of 9, 7, 0. No, sorry, 9. Sorry. The important point is PP2. Yes. Okay. No. Okay. If you look at the elements, okay, you see 9, 7, 0. Okay. If I compare two lists, okay. So I see 9. Ah. Okay. No. Okay. Sorry. If I have a list, I have only one constructor, which is const. But here I have two. I have two equivalent of const. I have the const version 1, and I have another const version 2 here. Okay, so it's okay. It's no longer exactly like a list. It's a little bit like a list because it is linear, but at each position I could choose this constructor or that one. Only at the end I have only PP0. Okay, so okay, so this list is okay. If you look at the number, you have 970 here. If you look at the number for the second one, you have 920, and here you have 420. Okay, actually, you should look at all the things, the constructor and this argument here. But anyway, you see that you have 3 different proof trees for the same conclusion, which is this one. Okay, so this is something which is more rich. But anyway, we can, for instance, prove something like this. We can prove that for all n, if n is even, then n is also P2, P4, P2, P7. Okay, because well, this is quite obvious. I can just use only this constructor. So the proof, what is interesting is how to make the proof. So what you have to understand is that the proof is not by induction on n. This would be wrong. If you try this, okay, this is here. So because n is not the right thing here. What is interesting is that you want to consider these proof trees. You will reason on this the way of constructing a proof of even n, and for each proof of even n, I can get a proof of P2, P7 of n. So you see, it is the important object is here. Okay. So how do you proceed? Exactly as usual, actually. It's just you have an additional parameter, but beyond that, it is exactly the same. So I introduce n and a proof that n is even. Okay. So I call it if n. And I will proceed by induction on this one, because you see that all the proof trees of even n are inductively constructed. It was the very point here. Okay, where is my okay? Here, if you see even, all these proofs of even something are inductively constructed. And again, we have seen that these are the object. These are objects like this. Okay. So I will reason on the possible proofs of even n, and the possible proofs of even n have this shape. Okay, so let us proceed. So I will say that I perform an induction on if n, and I have two cases as usual. Either if n has been constructed using the constructor E0, or if all this proof has been constructed using the constructor E2 with parameters some natural number, I call it n prime, a proof of even n prime, and as it is an inductive tree, okay, I gain an induction hypothesis on this thing. Okay, this is on this thing. Remember, again, look at the definition of even here. Okay, you see that it is even, which is okay. You can have a kind of recursive call if you want. Okay, so as this is something which is in the type you are defining, you get a induction hypothesis on this part, so which is called okay, if n prime. Okay. So I get two goals. Okay. So first goal. So the first goal says that okay. So intuitively, the first situation is that I had a proof of even zero. Okay. So if I had a proof of even zero, okay, sorry. I have a proof made with E0, and E0 is a proof of even zero. Okay. So in that case, what I have to prove is P2, P7 of zero. Okay. Because of this constructor constrains n to be zero. Okay. So in that case, I have to prove this one. Okay. Okay. So this is very easy. I just apply PP0 and for the second constructor, okay. So the second case. So I had some number n prime, a proof that this n prime was even, and an induction hypothesis saying that, okay, I was already able to make a proof of P27 of n prime. Okay. this one is not exactly written like this in my definition. I wrote 2 plus n prime, but you know that 2 plus n prime is convertible with this one. So I can change, for instance, change using the tactic we already learned yesterday. So, but it's not necessary, but maybe just to make things a bit more clear. Okay, so it is P27 of 2 plus n prime. You know that this thing can be proved from this using the constructor PP2. Okay, so this is yes. I will use this one. Okay, and now I just use my induction hypothesis. Okay, so this is very simple. And it is interesting because you are programmers, so you like recursive functions. Okay, so this is as this theorem is quite simple. It is even possible to write directly a proof of this statement in the shape in the form of a fixed point. So it is like this. So look at it. So I take n. Oh, here it is called En instead of Evn. Okay, maybe let us be more consistent. Okay, so I take a proof Evn of even n, and I will return a proof tree of type P2P7 of n. Okay, so what I do is to a pattern matching on this element here. Okay, so I will say that I have 2 possible cases for EVN. EVN could be E0, and in that case, as it is E0, n has to be 0, and so I have to return a P2, P7 of 0, and so PP0 does the job. And in the second case, for EVN, so EVN is constructed using E2 applied to some number n prime, and the proof of n prime is even here. Okay, and I just return. Okay, actually, you see it's kind of copy. It's kind of copy of the previous tree. Just translating E0 to PP0 and translating E2 to PP2. Okay, you have the same structure here, and here I make a recursive call in order to change the constructor. So you see, just like translating a linear structure made of E2, 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 E0 into another structure made of PP2, 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 PP0 at the end. So you see, it's exactly the same thing. Okay, and you can even execute it in that case. I think yes. So for programmer, I think it's at some interesting clarification. So I will compute this function I just defined here. So I have to provide a number. So here I provide 4, and I provide a proof that 4 is even. So proof like this: E2 of 2, E2 of 0, and E0. Okay. So let us compute it. And what I get, you see, PP2 of 2, PP2 of 0, PP0. Exactly. Okay. So you can imagine that the proof just in your head takes the previous proof tree that we had here. So you can translate it. E0 becomes a PP0, E2 becomes PP2, etc. Okay. So just to see that reasoning on proof trees is just a recursive program as usual. Okay. In that case, it is quite simple to do it by hand. In practice, if you look in the details, these functions here, use what we call a dependent pattern matching. So for more complicated situations, it becomes more difficult to write directly these functions here. So this is why, in practice, we prefer the interactive mode. Okay, in principle, it's possible, and personally quite. I happen from time to time to use this style, the style of the functional style for performing for doing proofs in some situations where induction does not exactly what I want. Actually, we have seen a situation like this at the very beginning when we considered the optimization for arithmetic expressions where you have zeros. Remember, we wanted to remove a number of zeros. When you have 0 times something, we wanted to. Okay, so it was still quite simple. It was not a proof. Yes, it was a proof because we wanted also to prove that that the result of the simplification of the tree, if you evaluate it, you get the same result as the evaluation of the original AST. Okay, so again, a direct induction would not quite work. So what can be used in practice is a mixture using the refined tactic. So, but in order to do that, you have to just to understand that you compute with proof trees. So usually you use induction, this kind of thing, destruct, and so on. So Coq helps you to to manage the dependencies in the right way. And from time to time, you may use refine because you want something more specific in the organization of the resulting proof trees. Okay. So, okay, so we could compute it and remember that the same thing is basically the same thing. You are able to transform a proof of 4 is even into a proof that 4 is a P2P set, P2P7, sorry. But this one has been defined with a QED at the end, so Coq is not able to compute it. So Coq will just say, yes, applying this function to 4 and to this proof returns a proof of P2P7 of 4, but I don't execute, I don't make the computation. I just keep it as is. Okay, no reduction. QED does not allow you to perform reduction. Okay. Usually you don't care about that because you are just satisfied that you have a proof of this. Okay. You don't really need this proof to be to be reduced. Okay. So this is also a proof. This is also P2. This function applied to 4 and applied to this is a proof of that. But this proof is not reduced in terms of constructors. There is a subtle point here. If you consider a very simple function that you already defined, so what could I consider? For instance, okay, okay, length, for instance. Okay, remember of length, 6 point length of. Do I have a list? I'm unsure. Oh, I think lists are predefined Coq. Okay. Oh, okay. Or add. Okay. And nat. Well, Coq will find it. Add. So something like this. There is something subtle to here. Match n with. If it is a 0, you return m. And if n is a successor of something, n prime, no, then I will return the successor of the addition of n prime and n. The point is that like this, okay. the point is that when you write this, you claim that n is a natural number. So this natural number is either 0 or s of n prime. Okay? But actually, if you write this, add, okay, define, okay, or definition, okay, let's okay, x add of add 3, 5, 6. The n you have here is not a 0 and is not an s of something. Sorry. Okay. Here. Okay. It is add applied to 3, 5. I don't have something here such as okay, no add of xy or I don't say that. Okay. So if I want to say that all possible numbers are considered, why don't why is this not needed? This third thing, and of course you may imagine many others, multiplications and whatever produce a natural number. So the point is that when you make it has nothing to do with fixed point. It has to do with pattern matching. When you write this, actually you claim that it is enough to consider the constructors. And why? Because when you perform this computation, you claim that actually the expression that will come here, this expression can itself be reduced to either a 0 or a successor. So this is important because it means that actually the fact that we define things by inductive types relates three things. You can define them, so it is introduction principles in logic. You can analyze them, so elimination principles in logic, okay, so destruct, pattern matching. But you also need implicitly, so this is something which is completely overlooked in many books, you also need the third component, which is that you can compute. If you cannot compute, it doesn't make sense. You can compute this expression, and after computation, you are expected to have this result. So the computation has to terminate, or at least to go far enough to have the first constructor, okay, to what we call the some head form, okay. So this okay. So if you consider computation that could not terminate, what does it really mean? I am sure. Okay. So okay. So so that's the same, of course. So here I considered just a very simple inductive type P and O natural numbers. But that's okay. So we do the same all the time. We do the same about proof trees, for instance, for this one. So I consider again here. Yes, I told that because here, okay, I cannot compute this one, but anyway, Coq says, okay, it makes sense, okay? So Coq cannot really compute, but it could compute it, okay? So it is just a kind of optimization inside Coq saying that, okay, we don't perform the computation in order to save some time, but it could be computed. It is just a matter of, it's not that serious, okay? We can really make this definition transparent like this one. And okay, for this one, there is no problem. Okay, the proof that we have here is okay. I mean, a proof of even is needs fine. Okay, is necessary in this form. Okay. . Okay, then okay, let us go to basic things. For instance, you can prove that if you have two even numbers n and m, then their sum is even as well. Okay, so as usual, we introduce things. So we get our two numbers. We have a proof of n even, a proof of m even, and I want to prove this one. Okay. So what could we do? So actually, the suggestion is written here. We just want. It is enough to reason by induction on even n. So okay, so exactly the same scheme as before, but for a more interesting lemma. Okay, so let us reuse the previous line, this one. Okay, I can exactly copy paste this one. Okay, and let's see what happens. So you see that I have to prove even of 0 plus m. Yes, why? Let us think a little bit. So if I E0, which entails that n will be 0, okay? So I will have to prove even of 0 plus m, okay? So this is exactly what I get. I have to prove even of 0 plus m, okay? So here, so you see that in that case, I just compute a little bit as usual, and I can use my previous hypothesis, okay? Exact. Alors, exact EVM, okay? Or second case, okay, so even blah, blah, blah. Okay, but this one, again, we can reduce it a little bit. So we get even of S of something. We know that in that case, we can use the constructor of even, the second constructor, which is E2, okay? So let us apply E2. Okay, I have to prove. Okay, so you see that this is very simple. I have my induction hypothesis here. Okay. Again, it can be interesting to see the functional interpretation of this proof. So you can do it at home. Okay. What else? Oh yes, this is exactly what I asked, what I said. This proof is simple enough that you can by yourself write the fixed point. So okay, I leave it as an exercise for you. And again, similar exercise, you can define the multiples of 4 as usual. Okay, so like 4 even, and then you can prove that any multiple of 4 is an even number. So in that case, you have to make a proof on the proofs of mul4. Okay, so I will not do it now. I think you have seen, you understood the mechanism to be used. So once again, there is basically nothing new, just reasoning on the different ways that some tree has been constructed. The tree happens to be a little bit more rich than usual because these are trees with parameters like this, okay? But otherwise, that's the same, okay? So we keep the same mechanism as before. So this is the strength of type theory. We have a very single notion of tree, okay, but somewhat more rich than usual. So trees may have many branches. They have okay, some depth and also some parameters. But that said, okay, everything reduced to pattern matching on trees. plus recursivity. Okay, and all the rest, I mean equality, disjunction, etc., are special cases, natural numbers, etc., are special cases of this single mechanism. So type theory. So the important point is that type theory is something where you have basic sorts and the universes, and then functions. Okay, we have seen the first day how function, so lambda calculus, okay, if you know about it, plus inductive types. And all these things works together. You can compute on values. You can also, this is an important point, you can also compute on types. So this is what makes the theory more okay, a little bit more complicated, but not. But still, you have a very uniform. How to say? A very uniform system. Okay, so I think that's all for this one. Okay, we can start now to the main application I want to consider, which is semantics of programming languages. Okay. So we will go into this file. And so this is the longest file, the file number 9 is the longest file in my material. So basically, you have almost nothing new. So all the basics, all the things you need have been presented, except one advanced topic. I want to talk more, maybe a little bit today, probably more in depth next week. So it is about what we call inversions. So we started to talk about this when we talked about discriminate, so contagious equalities. But there is something more advanced. So, but we will take our time when needed on this. So, okay, so let us go to the beginning of this file. So the beginning is, okay, basically what we have seen before. So we want to, okay. Here I import from the standard library a number of things, but actually I use only a tiny part of them. So, okay, it could be possible to redefine everything by ourselves. It would not be that long, but okay, let us save time. I will use the notation of list. I already told you on that. So list, okay, remember something like this. So list take a type and return the type. List of net is a set. Interesting. This is because net is a set. Okay. Print list. Okay, this is it is just a reminder of something which we have seen already. Okay. And okay, here's the way we can write a list using the notation. So 0 followed by 1 followed by 3. Okay, this is a tree, remember. And actually, Coq will present it in this way. It's large enough, okay. So with this famous semicolon, which is a little bit dangerous. Okay, but okay, this is quite common in OCaml, for instance. Okay, so what is here? So nothing here. Okay, so just proof by reflexivity. So let us go to the main material. So we have once again arithmetic expressions. Okay, then we have Boolean expressions which use arithmetic expression at some point here. Okay, and what else? And then the full while language. Here I added the while instruction. Ah, yes. Okay, we will see if there is something. Yes, I think yes. I think everything is here. Okay. I mean, there is a little point about functional semantics, but I think it is below. Okay, so now I define a notion of state. So just a list of that. By the way, I discovered by chance that in software foundations, they use another notion of state. At least in something which is derived from software foundation. So I guess it is exactly the same. I did not check but I'm quite sure it is the same. So, okay, this one is better, basically. They use something else. They say that so another possibility is to which comes from the theoretical books would be to say something like this: definition state is equal to yes, not to not, something like this. So, okay, so this one is a little bit, okay, be careful. These numbers represent the variables, the identifiers, okay? These are the identifiers. I don't want to add an identifier to another identifier. It doesn't make sense, okay? Okay, yes. You may add 10 to an identifier and you got something you have in the C language. I mean, you reason on addresses and you can make some how to say arithmetics on pointer arithmetics. Okay, so it could make sense, but okay, I don't want to enter into this kind of thing. I just want to keep very basic identifiers. So basically, just forget that these numbers could be added. It doesn't make sense. Basically, that we just need to compare to separate to discriminate between the identifier, say x3 and x7. Okay, there are different things. Okay, so the only point is that I have enough of them. Okay, and this not here means something else. It means the value which is in the memory set. So this one means address. This one means contents of the memory. Okay. Okay, so if you have this definition as a function, it looks nice because yes, it's a function. And if from a set theoretical point of view, you can, for instance, so the main operation, so you have two operations which are get and update. Okay, so get is just applying the function to an address and you get the value. Okay, that looks simple and sympathetic. And update, okay, so you take a function and you will say that I get a new function which is like the previous one. Okay, so you will say that, okay, let us write it as an equation. We will say that update, okay, some state with some, okay, some identifier, say I, and some new value V, okay, you will say that it is something like, okay, the function which says that, so which takes some other identifier J, and which returns something like, I will write in OCaml language. Okay, so there are no like that. Okay, so something like, let us put quotes. If, so actually I should say B equal, okay? So if E is equal to J, then I return V, else I return the previous function S applied to J. Sorry, sa fonction qui agit. No, this is J. This is this one, okay? Okay, something like this. So once again, be careful. It is okay. I mean, it is a test. Huh? Okay. I will use another notation for that, just to distinguish between the co-equal and the test, the Boolean equality. Okay. So you've had something like this. Okay, it looks fine. And set theoretical, from the set theoretical point of view, no problem. The problem is that when you have two problems with the definition. The first one is if you consider this kind of thing, update, okay, let a first state S1 is equal to the update of some state S0, okay, and then you make another update. Then, okay, update in S1, and you have another variable, so E prime, and another value V prime. Okay, and assume that I and I prime are different. Okay, so you could consider this one and this one. So you start I prime V prime, and here I V. Okay, so which means okay, first you update some address I with some value, then you update another address with another value in one order or the other. You would say that okay, you get the same function. Okay, so it's holds from the set theoretical point of view, but not from a computing point of view. These two functions are different. So the function you get here are different because they make the test in a different order. Okay, so it's a little bit annoying, and because you in practice you would say, okay, it's the very same thing. So why should we care about that? So if you want to use that, you need what we call. Oh, sorry. We'll put some comments here. Then if you want to do that, you need something which is called function are extensional. Extensional. It means that if you have two functions f and g such that f of x is equal to j of x everywhere, okay, for x, then f is equal to g. Okay, for x, I mean. Okay, so this is a basic principle of set theory. Okay, but from the computing point of view, that's not all. So you need to add this as an axiom. Okay, this can be done, but adding axiom is if you can avoid adding axiom, that's always better because the basic thing is that one axiom, that's okay. Two axioms, you run into problems. So you start with one, and then we are tempted to have another one about I don't know what. And okay, so they have this thing. Okay, so it's not very nice. And another thing which may be more important is that consider a memory, an initial memory. Okay, so you have a memory saying okay. With the values 3, 5, okay, imagine a memory, and then you update it. Okay, you run a program with loops and so on, and you make many updates, 1 million updates, because you have two loops with 1,000 rounds inside in each other. Okay, so you get 1 million updates, which means that after your loop, each time you want to access an element of the memory, it takes 1 million steps because you have 1 million tests to perform. Each time you have to be aware that each time you update a memory, then it takes one step more to access the memory. because you have an additional test. So as far as you make math, just reasoning, it is not a problem. But after that, if you want to say, okay, at the end, I have a nice semantics. I have, from all of this, I have programs which are based on that, and I would like to have a correct by construction program. So I told you that it is possible to translate from Coq to a real programming language such as OCaml. And then you will get something which is just unusable. So it is a bad choice. It is a bad choice. It is potentially a bad choice as far as, okay. Why? This is because in this kind of decision, you mix up mathematical considerations which come from set theory, like this kind of, so this thing, okay, from set theoretical point of view is perfect. But you mix up them with programming considerations, and then it does not fit so much. Personally, I didn't think I didn't even consider this thing because I am a programmer, and as a programmer, I am perfectly happy with this definition. It is just data. A programmer usually knows that we have data and we have functions, algorithm, and okay, we can do very nice things with functions if we are functional programmers, but it's not because you are allowed to write functions that you should use functions in a way which is stupid. Sorry. Okay. So this is okay. From a programming point of view, this is much better. With this, you don't have all these issues, basically. Should be a little bit more precise, but okay. Basically, okay, this one we have a little bit, but actually it can be avoided as well. It is we can have it if you go beyond. Okay, but actually, if you consider a fixed memory, this list is can be fixed. The length is can be fixed. So okay. So no real problem. Okay, so forget about this strange definition. Okay, and let us do things like we like them. Okay, so I have a state with okay this with two values, another state with two values, two memory cells, another state with three memory cells. Okay, just for tests. And okay, here is a program for the get program. I wrote it with a double pattern matching. I think I already told you. Okay, so no need to discuss more about this one. So we can play with it. Get. Okay, so just check that it returns the right thing. Update. So can be written basically with the same pattern here. So two things to be compared. So the identifier and the state. Okay. So my state is a sequence. And I have to be careful in this case because this one means that I am trying to access an identifier which is beyond the explicit memory. But usually it's better to have that everything is okay. We can make just to make this function defined everywhere. Okay, we just add 0 in the proper way. So okay, nothing very deep here. Just be careful. Okay. So let us check that if I update memory like this, I get what I want. Okay, so I think I don't no need to waste time here with that. You can take your time if you want. Now, defining the functional semantics of AEXP is very simple. So you just take your tree for your AST for expressions, for arithmetic expressions, and in each case you just call the right function for the corresponding constructor. Okay, and so basically you don't use a state except at one place, which is here for variables. Okay, so when you have an identifier okay, at address X, okay, but so you get the value in the memory, which is at address X. Okay. Now, for Boolean expressions, that is exactly the same. Just add two functions like here by maybe they are already in the library. I don't know. Okay. Anyway, we can easy to define. Okay, so true returns true, false returns true, and also all of this. Okay, and okay, just to show you that these two functions can be written in a very similar way, actually. Okay. True, false in the other cases, and recursive call in that case. And okay, and so eval b is written exactly in the same way. So this is infix notation here for the Boolean AND operation. Okay, so the thing is that you know, this is a way, okay, like in the C language, I think. So the disjunction of Boolean values, and these are our own functions just defined before. Okay. Okay, if we want to play, it is interesting to have some short definitions. So the value, the natural number, the constant zero, I mean, I give it this name N0 for short, and so on. For variables, it's what did I do? Okay, so I just say that the variable that I call X correspond to the address 1, Y correspond to address 2, and Z for address 3. Okay. So what do I have? For instance, expression 1, which correspond to X plus 1. Okay, so this X, so it will be, okay, I call it X and N3. Okay. So you just see that some tricks in order to have short expressions for what we have in mind. Okay. Otherwise, I have to write many constructors. So just a little bit of organization. So Y minus when it is A sub of Y and N1. What else? Okay, here maybe I yes, okay, so as usual, times 2, ME, okay. And so now we can compute expressions in a state. Okay, so you have to check that in the state I defined before, it returns the right result. Okay, so let us. Okay, I am just like a programmer. I make some tests in order to check that I didn't do some typo before. It's always a good thing to do. So I mix mathematics and programmer habits. Okay, a Boolean expression. So E1 is equal to N4. Why not? The negation of something. Okay. Well, okay, and we can play them. Okay, so okay, so nothing deep here. Okay, so now the interesting point. I would like to define the semantics of a program, a winst, okay, or some instruction, okay. And so I write it exactly as I would do in OCaml, so by a fixed point, a recursive program. So for skip, so I have a input state, assign xe, return the update in the state S for the variable at address X, and the value to be put is in the memory is the result of evaluating the expression E, so the right-hand side of the assignment, in the input state S. Okay, so you see it's quite easy to write. Okay, so this is the basic things. Next sequence. So I perform instruction I1, then instruction I2. So first I evaluate the the result, the state, sorry, I take the input state, I evaluate I1 in this state, I get a new state S1, and this S1 is the input state for evaluating I2. Okay, so I could also write using a composition of functions. Okay, eval W of etc. Okay, like this. Matter of style, that's the same. For the if, no problem. For the if, first I will evaluate E in state S. I will get a Boolean value. This Boolean value after reduction will be either true or false. Okay, so we could also write if then else, but here I want to make it very explicit what happens. So I evaluate, I get either true. In that case, I will evaluate the first branch, the then branch from input state S, same input state, and otherwise it is I2, which is computed. Okay, so nothing difficult here. Now the while, so the while first the same, I evaluate the expression here, the Boolean expression E, okay, in state S, and if these expressions, if returns true, okay, then, oh, okay, sorry, if it returns false, it's easier. I just avoid the while loop. I return the initial state S. Okay, it's like a skip. Now, if the evaluation returns true, then I have two things to do in sequence. First, a first round for the body of the loop. Okay, so the loop, the body is called I1. Okay, so I evaluate I1 in state S. I get a new state S1, and then I have to go back to the beginning of the loop. Okay, so I evaluate the whole loop. Okay, the same thing here. Okay, I evaluate it starting from the new state S1 that I got after the first round. Okay, so this looks fine. Okay, the denotational semantics. And I put a fail here because Coq will complain. So let us see what is the problem. So Coq complain. I added something that I maybe didn't tell you before. I make it precise that I expect this recursive function to do recursion on I. It is I, which is supposed to be structurally decreasing. And it happens, you can see here, for instance, I1 is a subtree. I mean, this I1 is a recursive call, is a subtree of this initial tree sec of I1, I2. Okay, so this is I, which is the main argument of the fixed point. So what is the complaint? Okay. Okay, so here it is just a copy of the code, so no need to read it. It is the same as on the left. So Coq says, okay, I have eval V, eval W, sorry, I, S, E, da, 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 da. Okay, so all the arguments. And he says that the recursive call to eval W has pre-simple argument equal to while E, I1. Okay, so where do I have this? I have this here. Okay, and he says that, oh, this is forbidden because here you make a recursive call on exactly the same thing. So it is not structurally decreasing. So it is not a fixed point for from a type theoretical point of view. For OCaml, no problem, but in this setting, we cannot do that. Okay, so he said that okay, you could use I1 Yes, I used I1, for instance, here. But here, I really want this one. If I cannot repair just by reading stupidly what Koch says and say, he wants I1. Okay, let us remove this one. I put I1. Okay. Yes, if I do that, yes, Koch will accept. Okay, the command has not failed. Okay, so I can write that. Okay, but it's just not the intended semantics. Okay, so so you not need to read what Cook says and just stupidly trying to repair it as suggested. You have to think what is my intention, and in that case, just no. The real thing is what I wrote at the beginning. So I have to accept that this definition is not accepted by Koch. So I have to proceed in another way. So the point is that actually, if such a definition was accepted, it would mean that I am defining a total function, a function which is defined everywhere. Okay? For any I and any S. And you all know that when you run a function, an imperative program, you don't define total functions because if you can have here a program which loops for some inputs or even that loops all the time. Okay, so this is very easy to define. A while true skip. This is a very basic program which says, which returns nothing. And of course, while true skip could appear in somewhere at a deep level or after if then else. So basically, you don't know. Maybe it never terminates. Maybe it terminates always. It always terminates, or maybe it terminates from time to time. But you cannot. It's impossible to decide in advance. It's a basic result of Turing. So that you cannot know in advance. I mean, at least by computation, you can know maybe by thinking, but by automatically it's impossible. Okay. So you have to accept that it is not the right way of defining the semantics of this such a language. So you have to do something else. And the nice thing to use is something that we just saw a few minutes ago in the first part of the lecture. So it's time to stop now. So we will use our inductive definition of relations. Okay, so this is called the big step operational semantics or natural semantics. Okay, so let us have a rest.
Nice place to stop.
Yeah.
If I on stage and you can define totally.
Yes.
But it has type of propagation.
Sorry, you mean this is the Koch equality or it is by definition? It is, I mean.
Is for all x fx equal to dx.
Okay. So we talk about equality.
Yeah. But it has type of propagation.
Yeah.
But how can I define it like net? They is a ball. But even not. Yeah.
That's exactly the point. Huh? It is the right point.
Right.
Yes. I mean, so for this kind of type, you are able to define a Boolean comparison.
Yeah.
But for not to not, or even even not to bool, which is simpler. Bool to bool, I have to think, because bool to bool is fine in some sense. But anyway, okay. But for true, for not to bool or not to not, as you want. And of course, from X to X or X to Y, you have, okay, so you take this and you would like to compare them, okay, you would have to test, this is what you want. You would like to have a comparison function between two functions. Is it your question? I just want to be sure that I understand your question.
I want to define
Yes, so you want to take F, for instance, from net to net.
yeah,
Okay,
next to net.
okay, that's something, okay.
Straight to net. Straight to net.
A state.
Straight is
Yes.
to net.
String. String. String to net.
String to net.
That's the same.
Yeah.
That's the same because okay, string are more complicated. Okay,
Yeah.
string. Okay, they are made of. Okay.
Yes.
But basically you can think that
Yeah.
it's simpler. Okay.
Yeah.
Okay. So we could say identifier to net. Okay, and identifier could be string or not or something. But anyway, if you have okay, something like this, and G is the same, okay? Okay, you would have some function test, such as, okay, which is a bool.
Yeah.
It's what you want.
Yeah, it is not.
No.
Oh.
There you know it.
Yeah.
There you know it because, okay, for a data, for string, that bool, list, binary tree, you can compare. You have data. You can, but for functions, you have what do you have? You have code, but it is impossible we have no access to the code. It is impossible to say, for instance, match this kind of F with and what?
No. Yeah.
You have no.
This definition is not good.
No. Okay, so you cannot compare two functions. So then one thing you could do is to what they do, for example, in software foundation. So okay, they take this, they say, okay, I am not able to compare function, but I am able to have this kind of thing. Okay, and then I say, I claim that if I prove that, then it is enough for me. So it works to some extent, but it's not very nice.
You mean that I can replace if this true, then output a true. Yeah. If this is true,
Yes.
if I can prove this, then output true.
Even that you don't even have that. Because okay, so you can yes.
Yeah.
Okay.
Yeah.
You can make a proof tree. You can reason and get a proof tree for a specific F and a specific J. But this for all is a prop. It is not a Boolean.
Yeah.
It's not a Boolean.
So
because you would need to make an infinite number of tests. Okay. If it is not, you need an infinite number. The for means an infinite number.
Yeah.
And okay, you don't have the time.
So when we said if I state as a function is not good idea. I think.
From my point of view.
Okay. Thank you.
Non, c'est vraiment, je me dis. Non, en plus, ce matin, je marchais un petit peu pour venir. Donc...
Moi aussi, j'ai marché.
Ouais, mais après, tu t'es assis. S'il faut, c'est debout et courir derrière un écran. Ouais, donc ça, c'est un des mauvais choix qui sont séparés. Et avec Alain, on a fini de regarder à peu près le code de Rand. Là. Il y a un autre mauvais choix qu'il fait, c'est qu'il utilise des types dépendants pas de manière incorrecte. De manière stupide. Parce que, tu vois, il a ses arbres de probable. Alors, on va aller chercher une avec une liste, etc. Puis au nœud, il dit probable. Okay, mais, donc, une probable, c'est un nombre. C'est un réel, donc ça, on peut en poser. Surtout, c'est un nombre qui est compris entre 0 et 1. D'accord. Et donc, du coup, son arbre, c'est un paquet de nombres avec des tas de preuves, pour chacun une preuve qui est compris entre 0 et 1. Après, surtout avec un paquet de nombres, c'est pas un autre paquet de nombres. C'est pas de dire, ah ben, est-ce qu'ils sont égaux? Ah ben oui, les nombres sont égaux, je suis content. Ah oui, mais alors, vu que les preuves, on n'est pas dessus, parce que les preuves, c'est des objets un peu embêtants. Donc, encore une action pour dire que proof ça s'appelle proof irrelevance, il dit que oh, bah, c'est pas grave, ok, ça marche, mais c'est un peu, c'est pas très malin. En fait, c'est la bonne façon de faire, c'est de dire, j'ai un arbre qui a que des nombres, et, parce qu'en fait, quand tu compares les arbres, ça veut dire que tu compares des nombres. D'accord? Pour encore comparer les réels, tu ne pas dans la même chose. Donc, tu compares tes nombres. Et puis, donc, la bonne notion, ce serait d'avoir un arbre plus un prédicat impossible qui dit que tous les nombres sont compris entre 0 et 1, si on a envie de savoir. Et quand on fait la comparaison, on ne compare pas les points, donc on compare les géants, ça suffit. Et on fait complètement idiot.
C'est bien que vous pouvez les.
Ah bon? Ah oui, oui. Ça, il y en a. Donc, les types dépendants, en fait, c'est bien, mais il ne faut pas les mettre dans les données. Il faut les mettre dans les fonctions. Dans les fonctions, ça, je suis géré. Les mettre dans les données, ce n'est pas une bonne idée, en fait. Bon, mais ouais, voilà, donc je ne sais pas pourquoi. Les gens de Software Foundation, ils auraient pu le dire quand même. Enfin bon, bref. Mais ce qu'il y a, c'est que, ouais, enfin, je crois savoir un peu d'où ça vient. OK, time to work again. Enough rest. Okay, so let us see the big step operational semantics. So actually, this relation is written according a very systematic scheme. Yes, I did not show it here, but I can show you the basic idea behind that. Maybe I have another file which is better which already explains the idea. Okay, maybe, okay. Sorry, I take a few minutes to check if I have this somewhere, because I think that on inductive relation, I think because I'm sure that I wrote that. Let's go back to this one. Logically, it should be inside, but maybe I made something wrong. In that case, it's not okay. No, not a big issue. I will repair it with you. Let's go to the end. Yes, I finished here this file. I am sure that there is some place where I have binary relations, because it's, the right point is to reason about binary relations.
You only have unary.
Yes, yes. To start with, unary relations are enough. You understand the basic thing, which is reason on. Okay, I'm sure that I have binary relations somewhere. Lesson is a little bit tough. Oh yes, we can take this one, which is one of the basic one. Though I have something on colors, which was which, yes, because my favorite example, it is simpler. Let me see. Sorry, I just take a few minutes to check that. Grep color, grep minus L color in equal.v. Ah, maybe it is this one. Maybe this one. Okay, it was there, but I just forget to to talk about this. I was too fast here, so sorry. I come back to this example here. I think I will not use the. Okay, so let us see. So yes. So I had yes, example on tail color, and then 5 colors. Okay, so the important here is place is here. Okay, so remember that we define a function from color to color, which said that the next color of green is orange, the next color of orange is red, and the next color of red is green. So we could perfectly define that using a function. Just say that I can define the same notion using an inductive relation. So this time it is a binary relation. So the very basic thing is that when you have a function from A to B, then you can translate it by a relation from A to B to prop. Okay? And here you get the set theoretical notion of a function, which is that it is okay. And it has also to be functional. So we will see that. So let us see. So next color as a relation now takes two colors, and you just say that, okay, I have the relation between green and orange, the relation between orange and red, and so on. So each time I give a constructor. Okay. So it is exactly what I was looking for here. And okay, so exactly by the same technique as before, we can prove that, for instance, if I have a relation between C1 and C2, the relation X color, then C1 is a TL color. Yes, because here I took color which is okay. The difference with the function I had before, here I take a color which is which could have seven values. Remember, it is the big color of this one. Okay, so here it is actually a partial function. So I am doing something different. If I want to define this using a function, it's a little bit difficult because I want this function to be defined only for green, orange, red, but it is not defined for yellow, blue, and so on. Okay, so in this case, the inductive relation is perfect. Okay, I only care with the domain, I say the values of the domain, green, orange, and red. So I say what is the return value, So in that case, no specific computation, no recursivity, this kind of thing. I could say it is an X color if, so I have an arrow before, I could have some condition implies this, okay? Well, in that case, I don't want this, but you could imagine that, okay? Okay. And that's all. Okay? That's all. So what happens here? Emacs is painful. I'm supposed to do what? No. Okay. Okay, so let us go now back to the previous. So 09, I think. Oh, my mouse is. Okay. So let us go back to this. So look at the type of this function here. So I put it on the top like this. So it takes a winst, a state, and it returns a state. Okay, winst to state to state. So exactly the same trick. Winst to state. So this is the two inputs, and this is the expected output. Okay, and you have a problem. So this time, okay, I can deal with partial functions. Okay, this function, this thing, the natural semantics or big step operation semantics is not always defined, but how it is defined. Okay, so you can see, for instance, that instead when I have S as an input, I have S as an output. It is exactly what I write here. When I have a skip and an S in the input, the output is S. So you see, it is exactly like a function, okay, but in the form of a relation. For the assigned is the same. For if my instruction is an assign XA, okay, here I wrote with an E, sorry for the different name. So if I take S as an input, the output is update exactly like here, except I had an E instead of an A, okay? Here, I think I put A for arithmetic expression. Okay, but maybe it is more consistent to have the A in the two places. Okay. And so on. So you see, I follow exactly the same thing. Maybe okay. So let us see for the sequence. So okay. So here you see that it is important to identify the middle state S1. Okay. So here I say that if I have a middle state S1, which so if I go from S to S1 using I1, and then if I go from S1 to S2 using I2, then I can go from S to S2 using sec of I1, I2. Okay, so you see that basically is the same as here, written in a relational way. Okay, so now let us go to the if, which is a little bit different. Okay, so the if is here. The if is written with a single case here, but from a relational point of view, it is better not to introduce a match. We will consider two cases, so two constructors. It is more convenient, but still very similar. So first case, eval B of an S returns true. Okay, so if it evaluates to true, if it is equal to true, then if I get S1 from S using I1, then the whole instruction, if B I1 and 2 will also return S1 from S. Okay, so this is okay. So the writing is a little bit different, but as usual, you always see the whole instruction, the initial state, yes, and the output state. Okay, so here the output state is S2 for the sequence. Here the output state is the output state of I1. Okay, so here I have two clauses, two constructors, one for when the evaluation returns true, and one for when the evaluation returns false. Okay, and now the case which is impossible to write using a fixed point. So let us put it on the top. Okay, maybe. Okay, we have enough room to see everything. Okay, so I start with the false, which is simpler. Okay, so if the evaluation of the test condition returns false, then the while BE from S returns S, like skip. And when the evaluation provides a true, okay, then first it is like a sequence. So from S, I go to S1 using one round of I, that's the body of the loop. And then this is here, I have no problem because it is not a computation, it is just a declaration. I say that if then using the whole instruction, I can go from S1 to S2, then I can go from S to S2 using the full loop. Okay. So it is exactly what I wanted to write using an algorithm, a program, but I couldn't because this program is supposed to terminate all the time. But here I just say, okay, I don't claim that for any input state I have an output state. I just claim that if, okay, I just claim that I can have from this input to this output using this program, and here are the rules. Here are the okay. So I make it. So if I am able to make a proof tree, okay, so it means that the program behaves exactly according to the semantics. Okay, and then we can do experiments like programmers. So I will, for instance, play with this program. So this program says while is not equal to 0, then I is decremented by 1 and x is incremented by 1. Okay, so a very simple program, but just to see. So some tricks in order to deal properly with variables. So I will have for each identifier, so I have two identifiers, I and x. For each of them, like in the C language, I have the left value and the right value. I don't know if you know this notion. So it just means that on the right of the equal sign, for the assignment sign, an identifier has to be interpreted as a value in the memory cell. But on the left-hand side, so on the right, it is a value, but on the left-hand side, it means the address. It means that I have to change the contents of the address at the address, okay? So in the same way, I will say, okay, I define first the left value. For instance, L will be at address 0, but the right value of I is actually EVA, the contents of the memory cell at this address, okay? And systematically, I use this way of defining things. So I correspond to the cell number 0 at address 0, and X correspond to the memory cell at address 1. Okay. So in this way, it is very easy to write a program. Let me put this in the middle. Okay, so for instance, I define a body loop. So the body loop is all this, okay? So it is a sequence of two things, an assignment and another assignment. For instance, the first assignment, the other is similar. The first assignment, you see the the I here, okay, I. So it is the left value of I, and here it is the right value of I, okay? And I subtract the right value by, okay, so I make this one minus n1, okay? And similarly for XL, okay? So you see that the program is still, this AST is roughly readable, okay? And then my program P1 is a while loop with an expression here, negation of the right value of I is equal to n0, and body loop, which is the previous definition. Okay, and now we can play with that and prove that P1, so this full program, transforms state S1 into state S2, state which has been defined before. Maybe let us see what they are, S1 and S2. Ah, here. Let us see. Okay, S1 is 1, 2, okay. And S2 is this one. Okay, so you see this is very easy because we will have one round because I is equal to 1, okay. The value of I corresponds to 1, and so X will be incremented by 1. Then we will get this state, and at this state, I would be equal to 0. So we exit the loop. Okay, so a very simple execution. So let us try it. So we can prove that P1 from input S1 gives the output S2. So not that difficult, not that difficult. So, okay. Okay. Let us like this, maybe. So we want to prove, okay. Okay, so this statement. Now let us, okay. So here I will be careful at not expanding too much because I want to see the exact which is needed. So I will just say that, okay, let us see a little bit what is P1. P1 is a while loop, with an expression and body loop. I don't want to expand body loop at the moment. So this is why I make a CBV with just P1, called value. So in that case, it is the right thing to use, okay? So now, what do I have? I have to have some knowledge about S1 to see what is in S1 in order to guess what will happen. So let us see what is S1. S1 is 1 and 2. Okay, so I know that I is 1. Okay. Okay, and maybe the same for S2 to guess, okay, 0, 3. Okay. Another way of saying CBV P1 is to say just unfold a definition. Unfold the definition and unfold and do some beta reduction on just before that. So, okay, application of function. Okay. Now, you see that it is a NS applied to what is important is the shape of the program. It is a while something. Okay, so as it is a while something, so it should be. I have to. Okay, I have to look at what. Sorry, I am here. Okay. Okay, it is. Let us put on this in the middle. Okay, so the conclusion here is like this: NS of while. So the only possible ways of concluding NF of while are here and there. Okay, these are the two possible rules. the other one conclude to something else. So I have to consider either this rule or the other. So now I have to guess what will happen. Remember, it is less comfortable as before. I mean, with function, I just have to compute. Here I can't compute. I have to understand what is the right rule. So I have to work a little bit more, but I can do that. So it is a while. So I have now to see whether it is this case or that way. So I have now to evaluate the condition here, B not blah, blah, blah. I have to see if this condition in the state here, the input state, will return true or false. So let us see. Okay, so okay, I can compute by in my head, but I can be more lazy. I have a computer, so let us just compute evaluation, the Boolean evaluation of my condition here. It's just a copy paste of this thing. Okay, let us compute it in the state. In the input here. Okay, so let us compute. Oh, it is true. Ah, interesting. It is true. So now I know that I am in this case. So the right rule should be NS while true. Okay. So I will try, but it will fail for a stupid reason. Not that stupid, but Coq will complain that he needs additional information. What is S1? Ah, yes, because it is a while true. And okay, so let us see how it is defined. Okay, got the control. So what could so we see that what I have in my conclusion, I have S1, I have S2, so I have, so this state is 1, 2, this state is 0, 3. So these two things are known. I have this thing, okay, so I have B and I, but this rule says that for all B, I, S, S2, and S1, blah, 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 blah. It means that I have to say what should be S1, okay? This is a kind of, okay. Intuitively, it says, if there exists some S1, so I have to provide a witness for S1. And now I don't know what is S1. So I could try to guess it, but S1 actually will be a consequence of computing knowing the semantics after one round, taking the initial state. Okay, so I will get the output state. So okay, so I cannot say apply. I can guess it. This is a little bit of cheating. Okay, so the way, the tactic to write in that case is apply with. Okay, so it works, but it means that I am able to guess in advance. It is a little bit too much to require from the user to guess the intermediate state. But okay, in theory, I can write it like this. So like in that case, Coq we will be able to, hopefully, we will have 3 goals. One goal which says, okay, check the condition, then find a proof tree for this one, and find a proof tree for this one. Let's see, it corresponds exactly to these 3 things here. Okay, I have to prove this thing. First goal, second goal here, third goal here. Okay, so I will have these 3 sub goals. But in order to do this, I need to provide S1, which is a little bit uncomfortable. So let us not cheat. And the first way to do that is to use our preferred tactic, which is refine. Okay, so let us say, okay, I know that it is an S while true, and I say, okay, so I have many holes to fill. Actually, a number of them are guessed from the conclusion, okay? And the rest, okay. Okay, so what we get is this. We will get actually 3 main goals, but there is something which is shelved. Okay, actually, if you look at the second goal here, it says, okay, I have to prove NS, so my relation between body loop, okay, one round, starting state, and intermediate state. Okay, so okay, so it means that actually this value, okay, will be provided if I am able to prove this thing. And actually, as it is a spatial relation, kind of functional relation, actually it makes sense. If I am able to provide a proof tree for this one, I will at the same time fill this small hole. Okay. So this kind of intermediate value, technically it is called an existential variable. Existential variable. So this is this E there. So instead of writing this one, which is a little bit long to write, you have to count the number of things which are here. 1, 2, 3, 4, 5, 6, 7, 8. Probably I have 8 holes. Yes, 8. I have 8 underscores. Okay. Okay, so no cheating, but okay. So instead of counting the number of arguments, I just say E apply, and okay, it has exactly the same effect as the previous refine. Okay, so E apply. So it is like the apply that I wanted to write here. So this one failed because apply is supposed to be very accurate. E apply is more tolerant and leaves some number of things to be filled later. Okay, but it is okay. It is very convenient for this kind of situation. So I say I know the name of the rule, and we will see later. Okay. So first sub goal. The first sub goal is just checking that the evaluation of the condition returns true, okay, in the state that we have. But we already performed the computation before to see, to know what is the rule to be used. In that case, I could just do CBN or reflexivity. So, okay, CBN would work, okay, and reflexivity. Now, second goal. The second goal looks a little bit strange because we have this existential variable, but okay, don't worry. It will be everything will be filled on time. Okay, so let us see what is inside this body loop. In this body loop, I have a sequence of 2 assignments. Okay, so as it is a sequence, no choice. Sorry, here it is a sequence. Let us check here. I have only one rule where it is. Sorry, this is yes. I am to. Okay, it is here. This is this NS-sec, which concludes by a sec here. Okay, and this is the only rule which takes sec as the first argument. Okay, so no choice. I will use this rule. Once again, this rule sec here, okay, is driven by S2 that I don't know, by the way, at the moment. So this one no problem. But okay, I1, I2, I have them as these 2 assignments here. But I have this S1, which is again unknown. Okay, no problem. Let us use just E apply NSSEC in the same way. Okay. E apply NSSEC. So I have now an assignment. And this assignment, okay, but I have only one rule. No, sorry, I have to jump. Okay, but I have only one rule called NS assign, which says that okay, if I have an assignment, blah blah blah, okay, then from the input state, I will get some output state. By the way, I get exactly the output state, it will be computed. Okay, so I just to say apply my assignment, and I get I know the answer. It is not computed, but at least it is expressed. The result, the first intermediate state is update of the state with this variable and this expression. Okay. So here, so not that bad. We can compute it maybe right now, maybe later. No, don't know. Okay. And okay, at the moment I don't compute. I'm not in a hurry. So LSSEC, remember, provided two subgoals, one for the first assignment and one for the second assignment of the sequence. So here I go to the second subgoal of the sequence, and here we see that now the initial state is update blah blah blah. So this is a little bit inconvenient. So let us compute now. I think this is the best thing to do. Yes. So I say CBN of eval A. Blah, 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 blah. Okay, all the things which are needed, or just CBN. Okay. So this one is very accurate. Okay, but let us just say CBN, okay, and okay, we get the intermediate state. So I started from 1, 2. The first assignment was a decrementation of I by 1. Okay, so you could see from I get a 0 here, and the second state is 2. Okay, so we see it clearly. By the way, if we had the state representation of the colleagues in UPenn, I would see something unreadable. Okay, I would see an update function. Okay, see, it is very clear. Just okay, just an array of numbers. I am a programmer. I like arrays or list, say. Okay. Okay. So now again, it is an assignment. Okay, so exactly the same. Another assignment from this input state. Okay, let us apply it. And okay, I get the full expression update. I will compute it later. Okay, so now I am in the body of, I finished the body of the loop. And again, I go back to at the beginning of the loop with the full statement. This is a while expression body loop. Okay, at this stage, I have this update, which is a little bit unreadable, but let us compute it. And I have now my new state, which is 0 and 3. Yes, the x has been incremented by 1. Okay. So I have a while loop, and okay, now you guess, because in this state, the expression will be evaluated to false. Okay. And then, okay, let us check it. Yes, it is false. So this time I will just use the NS while false rule, okay, and which will just check that yes, the evaluation returns false. Okay, so CBN false equal reflexivity, and it's finished. Okay, so you can see that actually the semantics. So when you explicitly write the proof tree, write the proof tree step by step. Okay, so it is just using the computation. It is like a kind of debugger. Okay, so nothing difficult. So okay, you could even see something I like to ask to my students. So I ask them to take a large sheet of paper and to draw the proof tree. Okay, a little bit okay, a little bit boring, but I want them to write it at least once in their life, so that they are really aware that they really manage through trees. Okay, it is a tree. It's a tree made of okay, a number of things. Okay, so you have fruit. Okay, in real life, we will not do that all the time, but at least once it is a good exercise to, okay, to understand what kind of objects you play with. Okay. Okay, so then next, some just for some.
Let's go back to the go back to the proof here.
Yes.
The loop body. Let's see. Loop body. Body loop. Sorry.
Body loop. Yes.
Go back there. Yeah.
This place.
Yeah.
Where? Okay.
Yeah, yes, because we need to figure out the intermediate state. We say you don't need to compute it, right? Yeah, it's here.
Yes.
And then how can we finish the proof flow? So we don't need to explicitly compute the state as well, right?
Yes. So what happens is that we will provide. We'll provide the constructor, the main constructor. We will focus actually on the main constructor of the proof trees. So the main constructors are NS-assign, NS-sec, this kind of thing.
Yeah, let's go one step. So NS-sec,
yes. So here I introduce another. Yes. At this stage, I have two existential variables. I have one called S10 here and another one called S1. Okay.
Yeah.
S1 comes from the while and S10 comes from the sec. Okay, because okay, okay. So the point now is that here I still have okay, I still did nothing, so I still have my two existential variables, but I see only one of them, okay, because I am in this subgoal. And now by just using this NS-assign, okay, this NS-assign will actually constrain the existential variable to be this, to be, or where it is. Here, okay, update, blah, blah, blah. Okay. Because, okay, so maybe how to, okay, I will try to show at the same time the rules so you can see what happens. Here, and assign, okay. Okay, this one, okay. So before applying the NSIN, okay, I had to my goal was NS. I had this NS assign, S was known, but here I had a question mark.
Yeah.
Okay. And this is how existential variables work. When I say, okay, but now I apply this rule, I apply this one, and by definition of this rule, then it constrains the last argument to be this expression, this term. Okay, so I get this term exactly at this point. Okay, so yes. Okay, so now I have it here. Okay, so it is not computed; it is just as is. Okay, but at least it is no longer a question mark. It is something Okay, because okay, okay, to put it otherwise, sorry, I'd like to have penable. Okay, I would like to have the two things together. No, not this one. This one. Okay. Actually, when I write apply NS sign, I say NS sign apply to X, to A, to S. Okay, so actually, okay, so the full refine would say, okay, it is refine of NS sign with, okay, the X which is given, I think it is XL. Okay, the A, I think it is A. No, it is because okay, sorry. Okay, no. What we see here is the next goal, I think. Is it is it possible?
But when you apply NSA, you should have two subgoals. Yes.
Yes, okay. What happened? Okay, yes, it is a little bit difficult. You have to be careful on what you read on the screen. Here I have two goals. Just before I have two goals. Okay, this one I will solve this one, and as soon as it is solved, I will see the remaining goals. I will see the goal 2 and also some other sub goals coming from the while. Okay, so the point is that when this goal is solved, S10 will be known. So I will the next thing I will see is this sub goal with S10. Okay, replaced by its real value.
When you apply S for the first goal, the first goal, you apply NS assign.
Yes.
And we don't need to explicitly provide a state for S10.
So we have 1, 2, 3, 4 arguments of NS assign. Okay. Okay. So let us see. We have sorry. 1, 2, 3. Okay, 1. Okay. Okay, you have okay. You have to look at the type of the result. Okay, so it is NS of 1, 2, and 3. Okay, so the three things you see here are 1, 2, and 3. Okay. Okay, so you have this kind of unification. Okay, so and the point is that in order to say that the conclusion is the same, so okay, so no problem for the assign. Okay, I have an assign, blah blah blah. S is 1, 2. Okay, but moreover, you see that okay, when you say that the first argument here, assign XA is this one, then you say that X has to be IL. You say that A has to be this expression, A sub. So S also is fixed, okay? So the things that you do when you say NS assign, you say refine of NS assign with X is the IL and A is this one, etc. So you fill this whole thing, these three things, and the conclusion is necessarily NS of this, that, and the third must be, so the third it is this one, the third must be this.
Oh, I see. So
okay.
So for the
So
you apply NS assign,
yes,
so
yeah,
this
so-
S10 will be bound to this
yes,
thing.
yes.
And then in the following goal,
Then,
Then
okay.
it will disappear to be.
Okay, and then is the next goal, as S10 now is known.
Yeah.
Okay, is known, okay, because just applying the rule is known. Then in the next time, you don't see this, but you see this expression with right instances of SXAS.
Because I thought we need to provide explicitly the value for SN, but actually we don't
So,
do that.
yes. So yes, if you do things completely explicit everything, but
Yeah, it's not necessary.
yes, it's not necessary. So see what I said before at that point when I explained things here. So the apply fails, but I could be very clever. Okay, I guess that the result is this.
Yeah.
S1. Okay, in that case, there is no problem. Okay, I need to prove that, okay, I will go from 0.2 to 0.3 and everything will be filled, okay, in the usual way. Okay. Yeah. Okay, but for it's more convenient to to keep a question mark here. Say, okay, I will guess this thing later, but okay, in some sense, okay, I go back. Okay, now I know. Okay, I can progress.
Mm-hmm.
So at the end, you have a proof tree as expected. Mm-hmm. Okay. So this is quite convenient for this kind of situation. Okay, now just the same proof. So the previous was a little bit long. I had a large number explanation. I would like to show you another way of presenting the proofs. So we have so usually I use bullets like minus and plus in order to it is important to organize a proof saying that okay I have goals, sub goals, etc. So when you change something, it is very easy to retrieve where a goal comes from. So another way to use curly braces, I will show you on the same example. So callable value, etc. Okay, and again here, I remember that in this situation, the Boolean expression will evaluate to true. So I know that I should apply to. Okay, so nothing new until now. So usually I should write minus first bullet. So I will think, okay, imagine that now you have a body loop which will be, which will run several times. So you will get a proof tree which is, okay, like this. And so you will get, your proof will go on the, how to say, so indentation will go very quickly to the right, okay? And you may think, okay, actually I have a kind of main branch, okay? I will focus, okay, each time on the main branch, which is each time the main thing, the loop. And I have a auxiliary branch, like, okay, checking that the expression is as expected, returns a false, I think, etc. I will have another branch for just run a body loop once, and then I will go back to the main loop. So, okay, so let us see. So instead of a minus, I just open a curly brace. I see the same, only one goal. Okay, CBN reflexivity. And I finish this one. At this stage, I see two goals. Okay, and again, I will open a curly brace and execute one round. Okay, CBV body loop. I recognize the sequence. Apply an sec. I recognize an assign. Okay, so apply an assign. Okay, I see my update. I compute my update. Okay, I apply my last NS assign. So at this stage, I finished my body loop, my first round. Okay, I finish this one. So these two curly braces correspond to what you can see here. These two things. Okay, I say that when I want to make a proof of NS while in this case, so I have basically three subtrees. I say that the two first are some kind of auxiliary proof trees for the first one, second one, and I go back to the main thing which is here. Okay, the full body, the full loop, the full while loop. Okay. Okay, for this one, now so I finished my second sub goal. Okay, CBN just to update my state here. Okay, okay. I think you can read or guess. 03, 03. And okay, so for this example, it's not very impressive because now I'm finished. Okay, I compute. Okay, I know that the loop is finished, CBN reflexivity. Okay, QED. But now if you want to do the same thing for okay, a more interesting case, so same program, but so this time I will have two body loops to for two rounds to do because the initial value is 2. So okay, this is more convenient to use the braces. Okay, so I do that. Okay. So that's all for a simple example. Now let us do more interesting things. For instance, I would like to prove a general theorem about P1. I would prove that P1 starting from any initial state xy terminates with a final state which is 0 and x plus y. Okay, quite intuitive because okay, I think it's obvious for you. Okay, to this effect, I will need a little bit of arithmetics. So here are the very basic lemma which can be useful. For instance, n minus 0 is equal to n. I think that, okay, we have two versions because depending on the version of coq you use, you can use this lemma or the same lemma, but okay, with a different name, but it doesn't matter, the result is the same. No, not the same lemma. This one has n minus 0 on the right, on the left-hand side of the equal, while this one, it was on the right-hand side. Okay, so depending on the version of coq you use, okay, use one or the other, okay, but nothing difficult. So let us go to the interesting part. Let us prove this lemma for trying to start the proof. And actually here, it is just, it is a little bit different. We cannot just execute because you see that the number of loops, the number of rounds, sorry, is equal to x. So I cannot make a finite proof tree just by executing as before. I need to reason on the possible value of x, and of course you will guess that x can be great. Okay, so I will make an induction on x. So here I will be careful. So okay, so a little bit of reduction, but an intro of x, and the point is that I will not do the introduction of y. So this is something I explained yesterday. When you do a proof by induction, be careful. In that case, I have to be careful because actually you see that y will change. So it is, if you introduce y will be fixed, and your induction will be impossible to prove. Okay, so you have to be careful. Say, okay, this y could change. Okay, so let us keep the y quantified, universally quantified like this, and let us prove this theorem like this. Okay. Okay, this is the trick we have seen yesterday. So let us, so the rest is as usual. Okay, induction x. So x is 0 or x, okay, here I keep the name x, and induction hypothesis. So actually it could be a x prime if you like, okay? X is the successor of this x. I will make the introduction. So it means the introduction of y, I think. And CBN of eval A, yes, because, okay, for some reason. Okay, so I prepared the work in order to see the interesting things. I have two goals. Okay, let us see. First goal. I think the first goal is not difficult. Okay, you can read here. It is 0. Okay, if I execute my program from 0 and any y, I will get the final state 0 and 0 plus y. 0 plus y, you notice y. And actually, you see that here you have the condition, you say that, okay, I have a 0, so I will make 0 rounds. Okay, so here, yes, that I will just actually, okay, I could compute, but let us just see that we will use the last. So it is called NS wild false, I think. Apply NS wild false. I think this one. Okay. Okay. So I have already the base case. Okay. Now the case where X is a successor of something, and I have an induction hypothesis saying that, okay, from xy, I can go to 0 x plus y. Now, I don't start from xy, I start from s of x, y, okay? So I start from s of x, y, I hope to go to this output state, 0, etc., okay? But you can, okay, think a little bit and say, okay, if I start from this state, s of x, I will perform the body of the loop once, okay? And then hopefully I will get a state where I will be in the state xy, okay, because x will be decremented by 1, okay? So it seems reasonable, okay? So this time I will just apply NS while true. Okay. Ah, yes, yes. E apply. Yes, E apply. What's this one? Okay, but okay, we see the message. Okay. Okay, eval B. Okay, well, let us see. No, plus CBN. Okay. Oh, effectivity. Okay, so great, it's reasonable. Okay. Now next, okay, we need to execute the body loop. At this stage, I think the induction hypothesis is of no use. I just apply my NSSEC, I think. No, NS maybe like this. Yes. Okay. Okay. Well, I could play with my braces. Okay. Okay, so apply NS assign. I hope it will be okay. at the moment, nothing. So I finished this one. Okay, next sub goal. Well, okay, I can put this for symmetry. So update. Maybe it's good to compute a little bit. Oops, sorry. Here I have something which is x minus 0. Blah, blah, blah. I would prefer to have a x instead. Okay, so I have the solution. So I think I should use this one. Okay, let us rewrite this one with a space here. Okay, and let us now apply NS assign. Okay, it's finished. Okay, and so last goal of last goal for the while for the while. So now okay, let us again compute the update. What do I have? I have my full loop x s of y 0 blah blah. You see that here I will use my induction hypothesis with s of y. Okay. So with f of y, I will get x plus s of y, not s of x plus s of y. Okay. So here I need this one. Maybe I could, for instance, right now rewrite this one. Okay. Okay, and now I can just apply my induction hypothesis. Okay, I think it makes sense to be explicit here. Okay, I could not say that, but I think it's better for clarity to be aware that we use this induction hypothesis like this. Right, finished. QED. So you see, I am able to prove an interesting basic property of this program without using whole logic. Just by running the semantics. Okay, so that's all. Okay, so we'll have a bit of time. Maybe maybe we can stop soon. I would just like show you a program that I like. This is the following program. I call it p square, which it computes the square of a number using only very simple additions, and not the additions like x plus x plus x x times. No, not like this. This one would be actually more complicated to prove because you would need a kind of invariant. Okay. So let us consider this one. So I have three variables, I, x, and y. Okay, I have these three variables, and I want to compute the square of n. Okay, so I start with yes, we need to start with I is equal to 0, while not is equal to I. Maybe. Oh no, okay, no. Okay, well, just like this. Okay, sorry. Okay, I start from a given initial state, but okay. Okay, so it would be better to write explicitly the initial state by adding some assignments at the very beginning. But okay, it is a very small detail. The interesting part is here. So imagine that you start from I is equal to 0. So I will be incremented by 1 until n. This is the idea. And x will be incremented by y, and y is incremented by 2. And the initial value of y is 1. So it is quite precise. And if you do that, at the end, you get the square of n. And you can, okay, just for your information, with just one additional variable and messaging the values here, you can also compute the cube of n or the etc. Just by a small addition. That's something I read in a funny book a long time ago. So I like this example. Okay, so just as usual, I will be number 0, x will be number 1, and y will be address 2. Okay, so nothing special. I have my 3 assignments. Assignment from incrementing I, an assignment for x here, okay, etc. So exactly, okay, what you would expect. Then a sequence of a sequence, okay, like this. And the full program is here while not okay, in this, okay, for this one, I compute the square of 2, okay. The square 2, so I check, actually I can compute 4. Okay, so while I different of 2, okay, run the body square. Okay, so as before, you can compute. Okay, you start from 0, 0, 1, and you see that you will get at the end 2, 4, 5. The important point is that you have 4 here. Okay. Okay. Okay, so I will not do that. So you can do, okay, find the program. Okay, so find PQs to find the right values. I think okay, okay. Okay, so in this file, I didn't consider the general square, but trying to prove that the square of n returns the square of n. But I will do that for the small step semantics. Okay, so I will consider the same program with the operation with a small step, and we prove. Okay, so now I will consider something else. Consider another thing, which is program transformation. Okay, so I will not do that today. So a simple from some program transformation is this one. It is just optimizing a program. Okay, when I have a if true, then x else y, I just replace it by the body of the then. Same thing if I have a false, just keep the else branch of the program. Okay, so you remove all the stupid if true and if false. Okay, and you could do the same for while, by the way. Okay, but yes, so you can do this by yourself. So skip doesn't change, assign does not change. I keep the I here. Sequence, recursively, I simplify the contents of the, okay, I call them W1 and W2. And here, of course, if I have a if, the constant be true, in my syntax, it is called like this. It is not Boolean, beware, it's not a Boolean expression which is true, because this would be undecidable. It is just simple. If I have the constant true, in that case, I just simplify 1 and return the result of simplifying I1, and so on. So just it's up to you to finish the definition. And then something which is perfectly feasible is to prove that if you have a program I such that an initial state S such that you have the expected input-output relation between S and S prime, then you have exactly the same input-output relation, but using the simplified program, okay, or optimized program. Okay. And how do you prove that? So before we have seen a proof where we reason on the state, we reason by induction on X. Okay, here is different. Here we will reason by induction on. Actually, we'll reason by induction on I for this one. Yes. Let me see. First. I think no, yes, okay. Okay, I try this, but I think that I observe that a number of things. Yes, okay. Actually, it is the same thing as for even. At first, we try an induction on N, and we are not very happy, actually. Okay. Do the experiment, maybe, okay, I don't know if I will do this with you next time, but anyway, you can try, and we will see something which is not very enjoyable. So we'll go back, and then actually the right thing to do is to do an induction on NS. The point is that actually, when you do an induction on NS, you at the same time it is actually like an improved induction on I, and because you not only you have you decompose I, but you also you are also constrained at the same time by the semantics. So we will see that it is the right thing to do. You will get a number of goals which are easy, okay, a little bit long to finish, but not difficult. So this is what is it. The proof is somewhat tedious. Later we will see that it is possible to share the tedious part in, using cleverly the semicolon, this kind of thing. And actually, you have only two interesting cases, which are when you enter in the if and in the false. Okay. Okay, so it's time to finish. So just to show you what you could try, because you will have time, because next lecture will be next Wednesday. So you have 1 week to play with this material. So really try. Basically, you should. It is not that difficult. So be careful. I have some numbers here saying, okay, this goal is easy, level 1. This goal is okay, a little bit more difficult. Still a little bit more difficult. When you see level 4, maybe okay, just admit okay, this kind of thing. And you are not. You can really okay. Try easy goals, backtrack, and then okay, it's up to you. Okay. And at some point, for a number of interesting goals, we will see a proof technique called proof. It will be one of the advanced topics I will consider next week. So basically, Koch has something quite nice for doing that, but sometimes it is nice, but not completely satisfactory. And I will show you how to do the same using only very basic constructs. A little bit like last time, we have seen how to perform discriminate using contagious equalities. So like a little bit more advanced, but reachable. Okay. And okay, just to conclude the program of what will come after. So we have seen that this function here cannot be written, okay? It cannot be written, but we can write something which is very close. The inductive, the relational version of this function. So I expect, I didn't do the exercise, but I have the technique for constructive, for writing in Coq a function with an additional argument which behaves exactly as expected. So the function will respect this input-output relation. I will add an additional argument. And if I extract this function, I will get exactly what we expect in OCaml. So you get a denotational semantics. Hmm? Yes, because the additional argument I add is an inductive definition saying that it can terminate in this situation. Okay. This additional argument will not be, it will be very neutral in some sense. I will it just say that, okay, if things can be arranged inductively, then, okay. Of course, if you want then to use this function in good situation, you need to fill this argument and say, okay, this program for this state terminates. Okay, it could be for a difficult mathematical reason, but by computing this thing, you get really a proof tree, and this proof tree allows you to execute the function. Okay. So this is the Braga method. So something, okay, a recent research result I got with a friend from Nancy. Okay.
Okay, thanks.
Thank you. So where is no? Oh, it's already stopped?
No, it didn't stop.
Ah, sorry. I'm always a stop share, yes, and then stop the meeting. At least stop for me. Yes, stop.